I presume we will have some presentations by the students, and I've asked them to please chime in and ask leading questions that might generate further discussion. Please be relatively informal, and we're going to start out, as was shown on the list over here, with a presentation from Ketan Bhatt on carbon nanotubes.
Good evening. I'll be talking about carbon nanotubes and different ways how you synthesize them and different applications. If you just go to any browser or any Web of Science subscription search page and just type in carbon nanotubes, you will get tons and tons of references. This is indicated in the way where in the end I have some papers for further readings and as references, and there's a whole lot of them. So what are carbon? First, I'd like to talk about what are different methods of synthesizing these nanotubes. So these are the three main methods listed here which are used to synthesize nanotubes. One is electric arc discharge, in which what you do is you basically have two electrodes, and under very high currents, which are of the range of 100 MPas, you basically pass that much current across it and you create this carbon. You basically evaporate carbon structure and form this nanotubes. The other thing is laser ablation, in which instead of applying high currents, you put in a high intensity laser and thereby vaporize the carbon. So these two methods require very high temperatures, going about thousands of degrees, from anywhere from 1000 to 1500 degrees Celsius, and it involves you vaporize carbon from solid state carbon precursors, which is mainly graphite rods. The other method which is in use nowadays is chemical vapor deposition, in which you use hydrocarbon gases and you deposit it on metal catalyst seeds, in which the most common seeds are iron or nickel or platinum. And this requires relatively low temperatures, wherein anywhere from 500 to 1000 degrees Celsius. So what are the types of nanotubes we get? One of the types of nanotubes are single wall nanotubes, and these are some illustrative images of the single wall nanotubes. On the left here you see a very web-like cluster of the nanotubes obtained by electric arc discharge. So in this case you have two electrodes. One electrode is graphite rod, the other electrode is a graphite rod with some metal inside. And when you apply charge across it, you get this deposition as it vaporizes, and this deposition is obtained on the metal or on the container. Once you wash it out with water, you get this nanotubes into liquid, and this is on the right there is a representative image of one nanotube bundle. So you can see that in one bundle there are about 5 to 10 different nanotubes aligned with each other. Now this alignation is due to the interparticle attraction between the two, or the capillary interaction between the two rods. And there are three main types of single wall nanotubes, and these are defined on how the material folds. So on the first, it shows this is a graphite sheet. Now if you fold this graphite sheet along this axis, which is written as zigzag, you essentially get some kind of this kind of a structure. This structure, in this case, all rods are semiconducting in nature. If you fold it across, when N and M are even or N and M are same, you get an armchair type of configuration in which all nanotubes are metallic in nature. If you do across any other than any other random orientation, they are called chiral nanotubes, and most of them have semiconducting properties, but the gap depends on the relative separation between N and M. If they are more towards us, the band gap is small. If they are more near semiconducting, they have a higher semiconducting band gap. The other type of nanotubes you get are called multiple wall nanotubes, and what you get essentially is you have a single wall nanotube which is again covered by some more graphite layers. So you get concentric alignments of thick wall nanotubes, and whenever you obtain multiple wall nanotubes, you get some kind of this structure or an array of multiple wall nanotubes produced. And if you zoom into this shows how aligned these multiple wall bundles are with each other. Now, going about this now, where can we use nanotubes as such? So I briefly put up some application where they are currently used. So one of the application is field emission. So you have any kind of a flat panel display. What you do is essentially you have different metal nanotubes on glass at different clusters. And when you apply electric potential across this, an electron is developed and it is emitted and it hits at this phosphor array. Now this leads to a electroluminescence or a color, or basically whatever it's called. And that way you get basically different colors. So in here, these are the flat panels which are currently produced by Samsung. And the main effect of this is they are easy to manufacture by screen printing. You can just print them onto in different desired shapes, and they do not deteriorate very much. They also provide stable emission. They have a long lifetimes and different other benefits. And it's very easy to manufacture compared to the current day flat panel displays which use either tungsten or platinum, or which one is it? One of those elements. So this is because of the semiconducting nature, sort of. The other application is, which is a very controversial application at this place, because no one knows what exactly happens in this case, hydrogen storage. So in here, what you do basically, if you pass hydrogen onto it, you can absorb the hydrogen into the nanotube as such, the capacity. And these are the storage capacities for different nanotubes. So the first one is for as prepared single wall nanotube. The second one is, the other two are pre-treated with hydrogen chloride. And what you see, it has a weight storage capacity of about 3% of each carbon. And the other important parameter is this residual H2 storage, which means that after you try to remove the hydrogen, the remaining hydrogen which stays inside. So you can leach out almost 70% of the hydrogen which you initially stored in the nanotubes. So this process, it assumed that it will be useful for fuel cells and different processes like that. And the other area of application is where you do biological interfacing with nanotubes. So this is a very simple example. What you do is, you have a single wall nanotube. You absorb this 1-pyrene butanoic acid ester due to the pi stacking, and then you do nucleophilic substitution with the NH2 of the protein molecule, and to get this absorption onto the nanotube. So in this picture, it's basically shown how the different ferritin molecules absorbed on a single wall nanotube. And this application may find use in different kind of sensors or biological detection elements and something like that. So with that, I would like to end my talk. And as I said, there are tons of references given at the end of the talk. If you are interested, you can go through any one of those and read through.
Use them all.
This referencing was useful done by EndNote, so it's easier that way rather than writing that.
Okay, thank you very much, Ketan. Do we have somebody who wants to start with some question?
What do you mean by NM when you talked about NM?
Nanometer?
No, N like...
Oh, N and M. Those are just kind of a nomenclature which is done for graphite sheets.
Yeah, but how does it...
I'm not sure how they do that exact nomenclature.
Okay.
I don't know. I'm not much into the other. It's something like probably some. I'm not sure exactly what that qualifies into.
Huge.
It's not definitely not huge, but it's comparable to current day semiconductor devices, as sort of. So I don't know what exactly that translates to.
Yeah, when you use those nanotubes for hydrogen storage, so they go into the individual tube. I mean the hydrogen molecule.
It's supposed to go inside each individual tube and stay there.
And people have actually started using them, or you said it's
right now it's
controversial?
still sort of a laboratory usage, and it's not anything like a commercial usage.
Yeah.
And all the values reported are also a bit ambiguous, as in some say that it's possible, others say that's not possible.
Yeah, I'm
But
wondering
it's
how,
one of the main areas of research currently, because if you can do that, it will be very nice, and it would be a good breakthrough sort of.
yeah, I'm wondering how much would be the pressure drop, because
I think I didn't put the pressure drop in here, but if you see here, this is the pressure drop per atmosphere per gram, sort of. And it varies from about 10 atmosphere per gram or something like this. There is a pressure drop which they see.
yeah, so
So
okay.
I don't know what this translates to physically as such.
Okay.
If you know, you can probably go ahead and explain.
Because recompressing is the major cost involved in most of these applications, right? So how much is the pressure drop? That will drive the
I think you
application.
should explain this to everyone. I don't know much.
Yeah. Why is the temperature employed low in chemical vapor deposition rather than
Because you already have it in vapor form. You are not vaporizing carbon. as such.
what exactly happens in the chemical vapor deposition?
What you do is basically you start with hydrocarbons, and most of them are something called a ferrocene hydrocarbon, which is essentially a hydrocarbon which has some iron into it. And when you apply, what you do is your catalyst is also basically metal iron. So this ferrocene molecule actually binds to that and starts forming this nanotube. So it starts forming a graphite structure on there.
What's the smallest size of nano?
I think it has been reported as small as 1.4 nanometers
1.4.
in diameter.
What's their length?
As long as length, they don't take it into a very big way, because the highest length is they have even gone up to 20 millimeters or so. Just by you can do some bulk processing, in which what you essentially do is start forming chemical vapor deposition and keep on pulling your sample away and away. So it forms, and you are basically extending it until it gets broken.
Well, I had a question. Why do these things form tubes? Why don't they form rods or something else? And if they form tubes, why don't they form sheets or very big tubes? Or
I think the natural structure is sheets, but just because they probably like to form and collapse onto themselves as such and form this rod kind of structure, or which are called tubes. They also have, like, these structures are also similar to what they have carbon nanorods or something which is close to that.
do they have a natural size that they tend to be a certain size, or do they sometimes larger?
I'm not aware of if they have a natural size, but most of the time, I think the natural size is somewhere between where the N or M is about 8 to 10.
Okay.
That's where it has been reported, sort of.
And then the other question, looking at it, is there's some structural similarity to buckyballs.
Yeah.
Yeah.
They are actually structurally similar to buckyballs, because buckyballs have like a 60 carbon structure and form a spherical structure.
They occur naturally too, don't they?
Yeah.
Any more?
Just on the same lines. And when do you form buckyballs? I missed the.
I think they are developed by similar methods, but in that you have like because carbon nanotubes were observed when they were trying to make buckyballs. So I think it's just some concentration driven or something like that kind of a process, which results, instead of forming spherical structures, you form tube-like structures.
Are the natural occurring buckyballs, are these like astrophysical observations, or is this somewhere here on Earth? Do people see buckyballs?
I think it's here on Earth. There is no astrophysical observance. I think it's here on Earth.
Sure.
Is it? I'm not aware of that. So.
Yeah. I read it in your book that you were reading yesterday.
What book? I wasn't reading any book yesterday.
What's it on your desk?
Okay, if that's all the questions, let's have a little applause for our speaker, who was brave enough to be volunteered to go first. And what we'll do is, I wanted to put up a revised, nicely typed up participants and topics list here. Here you can see You can see the accurate spelling of all of these names of the, and you can also see the full titles of the various things we'll be covering today. So our second presentation today will be by Chirong Fu from Wood and Paper Science Department over there on the corner of Dan Allen and Western. You're welcome to come over and visit us sometime. We're over there. We've got some interesting pilot equipment for pulping and paper making that you might be interested in. Some lab equipment that's very different from what you have over here, some of it, yes?
Does it smell like a pulp mill?
It's unpredictable how it's going to smell. You never know whether it's going to give us this nostalgic smell of money that they always talked about as I was growing up in a paper mill town. That's money you're smelling. You never knew, but sometimes they pulp up the most interesting things, agricultural wastes, other kinds of wastes that they make into paper because someone has an idea that they ought to convert waste products into paper. And whatever it is, we have some very enterprising technical service group that are willing to process it through our pilot plant. And sure, we'll take your money to do it. And, you know, this benefits the ecology, maybe, in somebody's dream. And we'll try it. And we'll see if we can make paper out of it. Sometimes the yields are very, very low, and it doesn't actually make practical sense. But we'll try it anyway, because they want to know. Okay, so our next talk will be Chirong Fu, and I'll let her introduce her topic.
Good evening, everyone. My name is Chirong Fu. I come from the Department of Wood and Paper Science, and today I would like to introduce the application of microparticles in the paper industry. In my presentation, I will first introduce the paper mill and the paper machine system, and then why do we use the microparticle additives in the paper machine, and after that, I will introduce the different types of microparticles, and then introduce the mechanism of microparticle system, and finally, I will introduce the microparticles effects. Maybe I think you are curious about where the microparticles are added in this large paper mill, and first I would like to introduce how the paper was produced in this large paper mill, and this section is the pulping process. In this section, we cut the wood from the foliage and then cook, and then converted the wood to the pulp through the pulping process, and after that, the fiber should be refining to give the fiber the more specific properties. And after that, in the stop chips, we add some filler such as the titanium dioxide or the drainage aid or the retention aid to the chest, and then the stock will discharge from the headboard to the functional wire, and after that, to form the wet sheet. After that, the wet sheet will go through the press section, and then go through the dry section, and finally get the dry sheet. And the microparticle system can be used in this functional wire. Okay. In this slide shows the addition point of the microparticle. Before the screen, the cationic starch is added, and after the screen, we add the colloidal silica here. But why we use the microparticle additive in the paper machine? Because we want to improve the dewatering, and also want to increase the retention, and finally we want to improve the paper sheet formation. This slide shows the how the sheet forming. This is the forming fabric, During the sheet forming, the fiber will settle on the forming fabric. But if without the retention, some fine particles can pass through the forming fabrics. This slide shows how much the filler will retain on the white. It shows that if without the retention A, the filler titanium dioxide maybe will distribute uniformly on the wire. And also you can get the lower retention, only 90%. But if we add some retention A on the stop, we can get the 80% retention. And the filler can also distribute very uniform across the Z direction. And next slide shows the different types of microparticles. The microparticles including the colloidal silica, such as the BM8720, and also include the bentonite, such as the hydroco O. And also include the micropolymers and the lignin-based microparticles. Those of these microparticles is the any particles, and the iron-based microparticles is the cationic microparticles. Now I will focus on the two kinds of microparticles. The first one is the colloidal silica. This slide shows the surface of the colloidal silica. It shows in general the colloidal silica has 5 nanometer diameter. In the surface of the colloidal silica, the hydrogen ion will dissolution from the surface, so the whole colloidal silica will contain the negative charge. This slide shows how the colloidal silica synthesis. The first material is the sodium silica, or we can call the water glass. The first step is to decrease the pH value. If we decrease the pH value below the neutral point, we can get the silicate gel. If we decrease the pH value more, we can the silicate gel has the less negative charge, so it's easy to collide and stick together. But if we control the pH level to the weakly alkali condition, we can get the silicate shell. The silicate shell is more stable than the silicate gel. This slide shows the different types of colloidal silica for the paper making. The paper maker know with the addition of the different polymers, we can add the different colloidal silica, the salt and the gel. This slide shows the bentonite structure. The bentonite structure is very different from the silica. You can see that the bentonite can be as thin as 1 nanometer, but the plate can be as wide as 500 nanometer. And then I would introduce the mechanism of the microparticle system. The first one is the electrostatic effects. The maximum drainage and the maximum detention can be achieved at the same time at an an average zeta potential near to the zero. And then the microparticle system can be affected by the surface charge. If we add the smaller particles, the particle has the highest surface area, so then the particle has the highest surface charge. So it's very useful to the microparticle system. And the second mechanism is the bridging. Before adding the microparticles, we should add the cationic polymer to the system. The one end of the polymer attached to the fiber surface, and then the roots and the coils of the polymer will stretch out and attach to another fiber surface. And after that, we add the microparticle to the system. Because the microparticles has the opposite charge to the cationic polymer, so the microparticle can collide with the polymers, and then the polymer will contract, and the water will expel from the polymer gels. And in this way, it can improve the drainage of the. It can improve the retention of the fines and fillers, and also it can improve the drainage and the paper formation. This slide shows the practical, the micro retention and the drainage system. The original stop contained the fibers and the fillers, and we add the cationic polyacrylamide to the systems. You can see it can form to the folliculated stop. And after that, when the stop goes through the screen or any other high shell force section, the fiber attachment will break up. And after that, we add the microparticles. You can see the microparticle can combine the small flocks to be the smaller, denser, and more uniform network structure. So in this way, it can improve the paper formation. Finally, I will introduce the microparticle effect. You can see from this figure, when we decreasing the size of the microparticles, we can get the less drainage time, so the stop will drainage very quickly. This slide shows the effect of microparticle dosage on the flock effective density for the precipitated calcium carbonate with the high molecule weight and low charge density cationic polymer and the microparticles. And these three additives is the bentonite, and these three additives is the silica. You can see we add the bentonite here, we can get a higher flock effective density. And so the microparticle system can improve the retention of the fine particles, dewatering, and the shear formation. And also the charge neutralization and the bridging force play an important role in the microparticle systems. That's all.
Okay, I can open up this to questions. I just wanted to point out that the actual title might be called microparticles in papermaking or something like that, so you can disregard what it says up there. And please ask for the microphone when you ask questions. And one of the rules is that Chirong has to answer it. I can't. Or Takao could answer the question too, but I'm not allowed to. Anyone want to start? You let her off that easy?
How are the flow properties affected by the addition of these microparticles when you're processing the paper? I don't know anything about this, how you make it, but I kind of figured out that there is some shear stress or shear rate applied to it, and if you're adding those microparticles to the system, then your viscosity is going to change dramatically, because you can gel what you're processing at that time. So how do those properties change with the addition of the microparticles?
So you asked the
Properties like
Is that-
viscosity.
Yeah,
and,
properties like viscosity or
a change.
yes, or the strength of
So it
fluid
will.
that you have there, or the material that you have there.
So it how to affect the properties of the system, you mean? Oh, viscous. No, I'm not sure.
Maybe I didn't understand well, but I thought
Viscous.
it's okay. No worries.
Any other questions?
If you go to previous slide.
This one?
In a slide with some figures to show the mechanism or process of this paper making. Before this.
Okay. This no.
Ah.
This one.
Okay. In the last step, it looks like the particles and the fibers form so ordered structure here. Is this like some self-assembly in our class? As you can see, the particles and the fibers in this solution or suspension, they are unordered in 3 steps, and
Yes.
when you add microparticles into this system, and they seem to form ordered structure, right?
Yes.
Is that exactly order microscopically? Microscopically.
It's a long range ordering.
Long.
Long range ordering. Is there ordering on the, that's what you're asking, right?
Yeah.
Yeah.
Long range ordering.
How to explain that one more.
Is this a 2-dimensional or 3-dimensional order?
I see it's a 3-dimensional.
Thank you.
More imponderable questions? Okay, well, I guess we should thank our speaker. I should just fill in that the correct answers to some of those questions were I don't know, and really nobody knows the answer to those, especially the long-range ordering things. One thing to appreciate is that paper making is basically a mess. We've got all kinds of sizes and contaminants and a lot of different things in there. So there's no way that we would have some long-range ordered structure like you might have with a monodispersed latex high concentration material. I think that we're up to Holly, if that's okay in order of process. Okay, we'll go with Holly Roebuck. And she will be talking about, I hope, synthesis of metallic and semiconductor particles on defined special shapes. Oh, defined special shapes.
Shingles?
Let's see.
Sharp objects?
I guess that's good. Okay, I'm going to be talking about shape-controlled synthesis of basically metallic nanoparticles. I didn't really do too much with the semiconductor part of it. So, And I wanted to start with the possible applications for these particles. And some of them include you can adjust optical or catalytic properties of systems. They can be used for microelectronics, chemical absorption, they can be used as photocatalysts and as sensors. So I'm going to focus more on the synthesis of them. And through my research for this presentation, I found that there were two main methods. You can vary the concentration of the reactants that you use to make them, or the capping surfactant, and that means you coat the particles with a capping surfactant to keep them stable, because if you don't have it, they'll just aggregate. And the second method is to irradiate it with UV light to form the special shapes. So the first example is the synthesis of silver cubes, and then they use the silver cubes to form the silver boxes. So the general reaction is the reduction of silver nitrate in the presence of ethylene glycol, and polyvinyl pyrrolidine is used as the capping material for this reaction. And they said that if you increase the concentration of the silver nitrate, you'll form these cubes. And if it's below 0.1 molar concentration of silver nitrate, you'll get wire shapes instead of the cubes. And then they used these cubes as sacrificial templates to form these boxes. And here's the reaction for that. And they converted the silver cubes to a soluble species, so that all that was left was the hollow gold boxes. And that's it. And the second example involves platinum nanoparticles. So they just reduced platinum ions in the presence of hydrogen gas with sodium polyacrylate as the capping material. And that they showed that changing the ratio of the capping material in this case is what affects the shape. And so they started off with adding 0.2 milliliters of a 0.1 molar sodium polyacrylate solution, and they formed these cubes. And when they added an additional 1 ml of that solution into the reaction, it formed tetrahedral structures instead of the cubic ones, which I don't have a picture of that. And this is another example of varying the concentrations of the reactants or just changing out the capping material. So for the first one, they used a 0.1 millimolar gold solution in polyvinyl alcohol and exposed it to light to form the nanoparticles, and you got these plate-like prism structures, which you can see in the first picture. And when they increased the concentration of the gold solution to 1 millimolar, they formed these hexagonal structures, seen in 2. And then they went back to the original concentration of the gold solution, the 0.1 millimolar, and then just used polyethylene glycol instead of the PVA, and they got these sort of ellipsoidal structures instead of the triangular prism structures. And this is an example of the second method where they used UV light to transform it into specific shapes. So in this case, they converted silver nanospheres into nanoprisms. And this is the general reaction for it. But the main thing is that they could, the reaction is initiated with the exposure of UV light in the 300 to 700 nanometer range. So it can be started or stopped anywhere in there just by exposing it to light. So you can, you can start it or stop it whenever you want to get whichever structure. So they showed that originally, it's kind of hard to see, but they were mainly silver nanospheres in A. And then after 40 hours, there's a couple of little prisms, like you can see a couple there and there, that formed. And then after 55 hours, you're getting a mixture of particles, but you're getting more and more prism structures. And then after 70 hours, it's mainly all prism structures, which you can see in D. And this just is varied based on the time that it's exposed to the UV light. And that was short and sweet, and there are my references.
I've got a question right off the bat, and that is,
Okay.
did they run a control in which they didn't use UV light and saw no change of
Yes,
shape?
they did.
Okay, that's good.
Because when they kept it in the dark, it didn't do anything.
So why do you get these different kinds of different shapes? Is it because of if you change the concentration of these surfactants, basically those are surfactants, different kinds of. Has it something to do with the self-assembly of the surfactants? And what causes the different shapes?
For just changing, like in this example from polyvinyl alcohol to polyethylene glycol, I'd assume it's just a different reaction between the gold in this case with the different capping materials. They didn't really explain it too much. They just said this is what happened.
Okay. Now, in case of platinum, I think
that was just they just increased the concentration of that.
okay. So that's what I was wondering. When you increase the concentration and you see different shapes of particles.
Mm-hmm.
So has it something to do with the sodium polyacrylate? Does it form micelles? And when you change the concentration of that material, the micelle shape will change, and that somehow changes the shape of the particles.
I didn't even think about that, but you're probably right.
I have a question. Why is it called a capping agent?
Because they take the particle and they just cap it, like surround it with the different surfactants. It's just kind of coated.
Well, they're probably presuming a mechanism. Maybe we should be skeptical about that as to, by using that term, they may assume that they know the mechanism before they've proven the mechanism. So that's one reason to be skeptical as an audience. On that, the different shapes when you're adding some kind of additive, one thing to bear in mind is that in crystal growth, it's known that the different planes of the crystal will grow at different rates, and that will determine these crystal shapes. So if you put in something that changes the surface free energy of the different planes, this could affect if a molecule is arriving from solution in that plane, whether it stays there or whether it departs again and governs the growth. There are probably a number of different ways we could think, other mechanisms we could think of, some of which might be like this capping, where we could imagine that the stuff is protecting that face from attack of molecules. Other questions? Yes.
Like you said about the concentration, so should the time make a difference, like how long they're kept in contact to her? As you showed, like in the last slide.
In this
Yeah,
one, the
why-
time did matter for the
But why
light.
but why should it make a difference? That's what I didn't understand.
They really didn't say. I have no idea.
Well, clearly a diffusion mechanism is going to take time. We don't know what else is rate limiting, if it's a surface process or if just diffusion is the limiting factor. Yes.
When they use UV light, do they actually damage the nanoparticles? Do they cause any photo damage as such and modify the material as such? Or do the material stays the same, just the shape changes?
It just seems that the shape changes and the material stays the same.
I actually have seen a little bit of Takao's presentation that he'll be doing next, and it'll be interesting to see if there's a relationship between the UV light and the size of these particles, because you'll see that there's a relationship between colors and particle size. So that's another thing we'll have to wonder about. Anything more? Well, let's thank our speaker, Holly, for her presentation. And if we can bring this back into view. We've got Takao Sasaki, and his talk is entitled Bright Future for Fluorescent Quantum Dots.
Okay, good evening, everyone. My name is Takao Sasaki from Wood and Paper Science Department. Today, I would like to talk about the fluorescent quantum dots. This is the outline of my presentation. First, I will explain a little bit about what is a quantum dot And next, go on to the characteristics of fluorescent quantum dot. And finally, I will show you two examples of the application to the biological labeling. Okay, why is a quantum dot? Quantum dot is a metal or semiconductor nanoparticle, and the shape is roughly spherical, and its size is from 1 to 12 nanometer. And the important thing is their optical and electronic properties is quite similar to those of a single atom. So that's why a quantum dot is sometimes called as a artificial atom. Quantum dot has been investigated since 1980s, and a lot of applications are also proposed. And this is a list of possible applications. And among these, fluorescent probes are the first successive application of quantum dot. So today I'll focus on the quantum dot for this use. A typical quantum dot consists of the group 2 and 4, or group 3 and 5 atoms in the periodic table. But the cadmium selenide capped with zinc sulfide is widely used in fluorescent probes. This is a typical fluorescent quantum dot. The core is cadmium selenide, and it can absorb the light, and the electron or the electron hole is excited from the valent bond to the conduction band, and it emits a fluorescent whose wavelengths correspond to the energy gap between the valent and the conduction band. Because cadmium selenide is quite sensitive to air and water, it usually is covered with zinc sulfide for protection. And another reason that zinc sulfide is used that it can also improve the fluorescent efficiency, because bond length of zinc sulfide is quite similar to that of cadmium selenide. So it can reduce the energy difference between the surface and the bulk of the core. It can result as it can prevent the electron deactivation without emitting. So as a result, the fluorescent efficiency increases. And for biological labeling, the surface of the fluorescent quantum dot is modified to give hydrophilicity and biocompatibility, and the bonding site to biomolecules. Okay, how to prepare the quantum dot? Actually, there are many methods of preparation, and this is just an example. The principle here is quite simple. First, the mixture of selenium and cadmium is injected into the organic solvent, and as the solvent is cooled, sudden nucleation happens, and in this condition the particle size is more dispersed due to the ostward ripening. And the next mixture of the sulfur and zinc is added to make a shell. Then it is separated, washed, and the surface is modified. For the biological labeling, this quantum dot have to be binded to a specific target, biological target. To achieve this, usually these biomolecules are used for this purpose. Biomolecule here could be streptavidin, DNA, or immunoglobulin, which can form a specific bonding to a target, to the other biomolecule target. And this quantum dot can be bound to these biomolecules with covalent bond, hydrophobic attraction, or electrostatic attraction. Okay, let's see the characteristics of fluorescent quantum dot. Actually, this fluorescent quantum dot is the ideal material for fluorescent probe. It has availability in many colors and broadband excitation and narrowband emission and good photostability and high intensity emission. In the following few slides, I will show you some these characteristics in detail. You can see that here's a nice color variation. Actually, this color is dependent on the size of the particle.
Looks like it
So-
depends on the size of the bottle, too.
Yes. As you can see, the larger the particle size, the longer the wavelength. So also we can easily adjust the size of the particle in preparation. So that means just you can adjust the color by changing the size of the particle easily. Several different quantum dots can be embedded in polystyrene beads. This can enable you to make thousands of variations in color. This picture is actually the example of polystyrene beads, which the different quantum dots are embedded in. This slide shows absorption emission characteristic, and the left hand of the picture shows absorption spectra. And this red line represents a conventional organic dye, and this black line represents a quantum dot. As you can see, the quantum dot has a very wide absorption spectra. That means if you have several probes in the same system, just a single wavelength light can excite all of the probes at once. And this picture shows the emission spectra of the quantum dot. Yeah, actually, this is narrower than the conventional emission spectra, and also it's very symmetric. So that means it enables us to use many probes at once in the same system. This slide shows the stability against the photo bleaching. In this slide, emission light intensity is measured over the time, and this green line shows the intensity from the conventional organic dye, which is one of the most stable dye, but it still gradually loses ability to emit the fluorescence over the time, whereas quantum dot just remain unchanged over time. Okay, I show the two examples of the quantum dot for biological labeling here. The first is an identification of different structure in the cell. In this example, two quantum dots are used. One is green color, and the other is red color. And green quantum dot is coated with urea and acetate group, which can specifically bound to the nucleus. On the other hand, the red quantum dot is covalently bound to the biotin, and actually this cell is treated with streptavidin. So, and this streptavidin can bound to the actin filament. So, as a result, this actin filament is stained red selectively, and also this nuclei is stained green selectively. In this application, the cancer cell is detected by the biological labeling. First, cancer cells are incubated with antibody, which can selectively combine to some kind of protein which is specific to cancer cell. After that, quantum dot conjugated to immunoglobulin is added. Then this immunoglobulin can bind to antibody. And finally, you can see this green circle around the cell surface can be detected. If the different kind of immunoglobulin here is used, this cell surface cannot be detected. So actually this antibody is specific to this protein. So you can detect the cancer cell using this system. Thank you.
Okay, turn on the microphone again and see if anyone has questions. Yes.
You had mentioned that Oswald ripening was part of the growth mechanism for the colloidal synthesis of these particles.
Pardon?
You had talked about Oswald ripening and the colloidal synthesis.
Yes.
Yeah. How does how does that work exactly? Do you know? I mean, this is a diffusion controlled process, and why? So some particles are kind of growing at the expense of other particles. Is that the sort of the Oswald ripening effect here with these solid metals?
Yeah, I think in this process.
So the smaller particles might have a higher solubility, right?
Uh-huh.
I mean,
Yes,
look at
yes.
the Kelvin equation.
Yes. In this case, maybe this solution is supersaturated. So many nuclei is generated at once,
Yeah.
and it can start to grow. But maybe some nuclei is generated after several times. But this nuclei can shrink to the. You mean?
You're talking about maybe nucleation
Yes.
occurring throughout the entire reaction, or
Mhm.
something like that. But I mean, that aside, I mean, just Oswald ripening. To me, I'm trying to reconcile how this works with with metal particles, and how you can relate that to, for example, I mean, you might be able to model this growth mechanism as some sort of diffusionally controlled growth, some like T to the 1/2 type change in the radius of these particles, right? And so how would you be able to factor that into the material balance, for example? That do you have any idea?
It's different than Lipschitz coursing. It's not the same thing.
Maybe someone can explain it to me. 'Cause
Oswald ripening is different than coursing by the Lipschitz mechanism, like LSW equation.
Right. I'm not familiar with Lipschitz, but I mean, how does the Oswald ripening factor into these growth expressions that you can think of? I mean,
Actually, I don't know how much nuclei is generated regarding to the reagent you add or something, but just in my understanding, just post-word ripening condition, the big particle only the big particle can grow.
right. Usually, you think of Oswald ripening as okay. The smaller particles are more soluble,
Yes.
or they have a higher pressure than the larger
Yes, yes.
particles. We're talking
Yeah.
about bubbles, maybe.
Uh-huh.
But here, you're trying to grow uniformly sized
Mhm.
suspensions
Yes,
with narrow sized
Yes.
distributions.
Right.
And it seems to me that I wonder how this Oswald ripening effect could happen, because it seems to me like it's sort of a function of their diffusion boundary layers overlapping. And in a suspension where all these particles are floating around, in a sense that effect would be modulated in time, because not two particles of different sizes with different solubilities would never spend a significant amount of time with each other. So that effect would be tempered. And Oswald ripening is sort of like the opposite of what you want. You get smaller ones shrinking and bigger ones growing, which doesn't lead to narrow size distributions. I'm just a little confused.
Let me jump in here. Let me jump in here because I happen to do my PhD thesis in a group that was studying this very thing and these growth mechanisms that lead to very uniform particles. I think the answer is that there are two different mechanisms that have been sort of alluded to in this discussion. They're both true. that the Ostwald ripening probably is true in the very beginning phase. You reach the point of supersaturation, and some of the particles are just a little bit too small. They were a little bit late, and then as the supersaturation is decreased because of the particle growth, now it's below that critical level of supersaturation that can sustain itself and build up the small particle, because the sites on the surface of that very small particle are too active, and the particle, the molecule or the atom on the surface of that will tend to diffuse away. And so just with equilibrium, that one will tend to get smaller, whereas if it's a little bigger, the surface is a little more planar, and the energy is not quite as active on the surface, and so it'll tend to stay there enough so that that one tends to grow. And then once you get beyond that, once you get beyond that, then you're in a growth phase where I don't know the details of the reactions, but I'm assuming that the mixture gradually interacts and forms an intermediate species that builds up in solution and continues to build up at some level of supersaturation, but not enough to create any new seed crystals. And so the growth occurs only on the existing ones.
Do you quench the nucleation by dropping the temperature? So that's how you sort of try to promote instantaneous nucleation over progressive nucleation.
Okay, well, I've shot everything I know about it, so I'll have to assume that your mechanism probably is correct.
I don't know. I'm trying to pass proposition right now. This
Yeah.
is essential to figuring out the questions about philosophy today, so I'm trying to understand it.
Well, it sounded good to me. Your question?
I have a question regarding the size of the particle and its color. Were those homogeneous particle or the particle covered with this zinc sulfide layer? Yeah. So these particles, do they have a coating of zinc sulfide?
Yeah, this has a coating, but actually this color is only dependent on the core part.
So
Core part is
so it's the size of the core part, right?
yeah, yes.
But you do have the coating on all of these particles.
Yes.
Okay. And this size effect, how is it related to the color? Is it related through the change in your what extinction coefficient? I mean, what is?
It is said that it's changing the energy gap between LUMO and HOMO by changing the size.
Yes. Yeah. I mean, so that will give rise to the color. And why does it change? So is it a my question is it a quantum effect or is it a size effect? I mean, can you decouple them?
Actually, I'm not sure. But
Okay.
maybe quantum effect is because the electron is confined in the very tiny space in the particle.
Got another question back here?
What exactly is CDSE? These are two metals, right? Se is a yeah, but how do we form this? Because Se is metals usually cannot be negatively charged. One of them has like how is this formed? CDSE is this?
We were just
I'm not sure about that, but this is actually a crystal.
I'm sorry.
Yeah, these are the crystal.
These are crystals.
Crystal,
Right, but
yeah.
crystals like.
I think that, Takao, do you remember that when you were looking at the periodic table, you might be able to answer the question another way? She said that the two metals usually can't combine. I don't know if that's true, but the other way to answer that question would be to look at the periodic table and see what these two things are considered to be. I don't know if he has a periodic table here.
Actually, he's looking at polar electronegativity.
Yeah. The selenium is not necessarily considered a metal. It's like along the borderline there.
Okay.
I don't know, though, that your statement was true or
I've
not.
never seen.
Well, you have
two
amalgams,
metals.
so.
Sure, they have metal cores with gold in the middle and platinum on the outside.
Okay.
What are source materials? That's one.
How did
That's
they
different
get
from-
connected?
Huh?
That's different. I mean, that's
She's talking about
This is
a compound of two
Yeah, it's a
metals in
compound.
some
That's
kind of
a-
fixed ratio.
Exactly. That's exactly.
Which, you know,
This
if
is
it were
not
two
something
metals,
like
that
not
would be
two metals,
strange.
Yeah, they're connected. It's a metal compound. So
You can have an ordered solid solution.
okay.
So
Well,
it's,
the-
they're
the-
not, it's in a lattice. So
The point here is that one of these is a non-metal, but then when we look at some of these here, indium arsenide and indium phosphide, arsenic is usually considered a metal, but they're borderline.
you heard metallic bonds?
What is an
It's
alloy?
different than a covalent bond or
Ionic bonds.
an ionic bond or something
I've
like
never
that.
heard of metal bonds.
It's solid solutions here, but it's
We're very quickly getting into metallurgy here, and that's way beyond my field. Maybe it's not beyond Takao's field, but he's willing to talk about anything, I think. But- Okay, I think we should thank our final speaker, and thank you for your attention.
Sure.